But
Yeah,
you agree now.
Okay, so Nima will give his third talk today, and then we'll have a little bit of a change of a schedule tomorrow because we have another superstar for this week, Freddy Cachazo. So he will actually give the fourth segment tomorrow.
Switching topics a little bit.
Okay.
Actually, so this is great because given that I was proceeding at 1/3 pace compared to what I thought it would actually be, I think I can finish something. I can finish something today, and it makes sense to finish it today. So and not attempt to actually do a bunch of computations. So what I'll try to do today is finish defining the object we've been talking about, and tell you what the object is at loop level. We'll do that in a second, but first I'll talk about how to actually convert the geometry that we talked about before into actual numbers, into amplitudes. Okay. But again, remember the attack that we've been taking is to just think about this purely mathematically. So we got to the point where we have polygons. And we're talking about the inside. We decided to talk about the inside of polygons. And this idea generalized to this space that lives inside GK plus M or GK plus 4 as far as physics is concerned. So alpha runs from 1 to k, A runs from 1 to n, and this I runs from 1 to k plus 4. That can be anything even, but for physics we want 4. And so the space of y lives in GK plus 4. So in this case it was y equals CA ZA, where I runs from 1 to 3, and A runs from 1 to n, and the C's were inside the positive G1n, and the Z's were inside the space of positive matrices M3n, and the Y's lived inside the projective space G13. And this extends to the Y's that live inside GKK plus 4. The C's live in the positive GKN, and the external data is in the space of positive matrices of K plus 4. So this carves out some region inside GKK plus 4, the analog of the polygon, with some curvy thing. And as we discussed, in the case of the polygon, you can triangulate it, for instance, in that way. And you can think of each triangle as being the image of one of the two-dimensional cells of the positive G1n. And a nice triangulation is a way of covering the polygon with non-overlapping cells in that way. So similarly, we can take this space and we can cover it in terms of 4K dimensional cells of positive GKN. And remarkably, the 4K dimensional cells of positive GKN that cover the space are exactly those cells that occur in the BCFW recursion relations to calculate the triangle. So each term of the BCFW recursion relations adding together, what they're adding up into, what they're representing, is something that actually perfectly triangulates the interior of that space. So tree amplitudes, we still haven't figured out how to get the actual amplitude out of it. Well, from this point of view, but that's what I'm coming to in a second. But this space is the space in which all the VCFW terms naturally glue into something, and in that sense, the tree amplitude is the answer to the question of triangulating that space. In a second, we're going to say it more sharply. We're going to say that the tree amplitude is actually the volume of that space, but we have to define what we mean by the volume appropriately, which we'll do in a moment. And we also saw yesterday that independent of knowing about VCFW recursion, just from the definition of this object as it is, we could conclude where the boundaries of this guy were in GKK plus 4. The boundaries were when that k-plane intersected zi plus 1, zj plus 1. That was locality. And as we approached the boundary, we saw the beautiful consequence of these positivities that this space splits. The boundary literally splits into two pieces, which look like the lower tree amplitude problems on one side and the other in a way that exactly looks like what it's supposed to look like for the factorization of tree amplitudes. But that was all a feature of the geometry yesterday. We still haven't seen how to get numbers, how to associate numbers and formulas with the picture. And so the first thing I want to do today is talk about how we get formulas associated with this picture.
So before you go on, so how many subregions are there that are always fixed?
Oh, there are many. So there are some. So for these tree amplitudes. So first of all, independent of triangulating all of them, you can ask, do we understand all the cells of the positive Rashomonian? All of them. And that is something, I haven't explained it at all, but that's something that is now very well understood. It was described in a way that's accessible to physicists in this paper we wrote back in December. But every cell of the positive Rashomonian is understood. They're all associated with these on-shell processes. They have lots of interesting interpretations back and forth. So in other words, all possible ways of making k-by-n matrices with positive minors are understood. Okay? Now, the thing which is new here is that every one of those cells now is an image in GKK plus 4. Okay? And even the very top cell, the one with no constraints on it at all, other than all the minors being positive, it has an image in GKK plus 4. The image of that guy is the entire amplitude in that case. All right? But as we go down to lower and lower dimensional cells, the space-filling ones are the ones that go down to 4K dimensional cells. So 4K dimensional cells of GKN correspond to different looking regions inside GKK plus 4. When it was a polygon, or more generally when we're living in G1 something, they all have the same shape. They're all triangles, so they're all simplices. So the positive G1n is particularly simple. The positive GKN in general for higher K is not so simple. There's lots of different shapes. So there are many different building blocks that you have to use to a triangular cell. Now you can ask,
always the same number of triangles
needed to cover it. Is that the question you're asking?
because the amplitude I thought was a given amplitude. So you know how many terms you have to add to get the full amplitude.
Well, so that turns out to be true, but it's quite non-trivial, and it's not. We don't even know exactly why it's true. I mean, if you use VCFW recursion relations to get the amplitude, then yes, the number of terms is fixed, and it grows. Like for the first really new case is k equals 2, n equals 8, the 8.n squared tree amplitude that was computed very on by Fredian terms as the use of VCFW, and that famously has 20 terms. Okay? So there's 20 terms. Every way of doing VCFW will give you 20 terms. Right? The 20 terms are different. Okay? You swap them around. Now, of course, we know that there are other ways of doing triangulation that don't look like VCFW, okay? But they all involve more terms and also some minus signs. So somehow what they're doing is overcovering some region and then subtracting some parts out. Okay? So for these tree amplitudes, there is something extremely canonical about the way VCFW covers them. So if you just wanted to triangulate them nicely, there's no nicer way of triangulating them than VCFW. Later when I talk about there's no unique triangulation, of course. There wasn't even for the polygon. So yes.
By cells of G plus Kn, sorry, what do you mean of that?
Cells, what I mean is that we can have all the minors positive, And that's the generic configuration. Now, some of the minors can be 0. And that means that you're going towards the boundaries of positive GKA. Just like when you have the inside of a simplex, you can put some of the C's to 0 and you go towards the edges, and you go toward the faces and the edges and so on. So because they're not all triangles, you don't call it a triangulation, you call it a cell decomposition. Not you, they call it. People, professional people call it a cell decomposition. Okay? So cells are just, but there's a notion of dimensionality. You know, how many constraints have you put on it? And so if we say that means that there's some way of parameterizing positive matrices, let's say with only 4K variables. Okay? And those ones map into some space-filling region in GK plus 4. And yeah, the interesting thing is that the BCFW terms just cover the space. They don't intersect each other. They beautifully cover the whole space. Okay. All right. So, but as we'll go to loops towards the end of this lecture, we extended the BCFW recursion relations to loop level in this theory a number of years ago. And while it's been wonderful to have that extension, allows us to get the right answer, it's systematic. It's also fair to say that there's a lot of structure in it that it's pretty opaque, and we don't really understand very well what those what it looks like at loop level, much more poorly than we do at tree level. The picture that I'm going to give for what the object is at loop level, so we'll still have the feature that the BCFW terms are like the triangles, but I mean, that's just sort of empirically true, observationally true, but we don't understand very well how it works. And it's also the case that we can sort of directly triangulate the objects at loop level without determining them recursively. So while at tree level we know for a fact that I would bet anything that there's no better way, no more minimal way of triangulating these spaces than the BCFW. At loop level, it isn't obvious. And certainly, the ways that we go about doing the computations don't look anything like loop level BCFW, and yet we get the same answers. So, there does seem to be something new going on at loop level, which, even from the BCFW point of view, we suspect, because when you calculate these things recursively, if you want to calculate the 2-loop 4-point amplitude, you have to start from the 8-point tree amplitude and take certain limits, and lots of terms vanish, and it's not clear why this vanishes. Anyway, there's a lot of structure to it, so there's a lot more that needs to be finished. Okay, but let me now, just at this level, tell you how we're going to associate a function with this space. So we're going to think of the z's, at the moment we just have a space. The z's are external data, and this is just I give the external data and I have a shape. Okay. But now I want to get something that depends on the external data, on the z's and integers. And the intuition is to just go back to the polygon and think, surely we can talk about the area of the polygon. Now, there are a variety of ways of, and why are we thinking about the notion of area? We're thinking about the notion of area because somehow triangulation gives us a picture that we're adding up to the same area. If I add enough some other way, I would add up to the same area, right? Area or volume has an additive nature. If you have two regions that are disjoint, and the volume of those of the disjoint regions is the sum of the volumes of the regions. And if they share a boundary, then the same thing is true. But if they pass through each other, it's not true anymore, right? So when we have the notion of area, that's really what we want. It's that additive feature that it has, which is a thing we like. And now I could motivate what we're doing by literally talking about an area, and then finding a closely related close cousin of that notion of area, which is this form we're going to talk about. But what I'll do instead is actually directly define. I'll really just directly define the form, and the other way, tell you what the connection is with the more intuitive notion of area. But before anything else, there's one thing that's obviously wrong with the notion of area, which is it has units, right? The area has units. So that seems it's not a very projective idea. The area is not a very projective idea. Everything here is very, very nicely projective. So that's a little bit wrong. That's something a little bit wrong. So we're going to do something a little bit different. Let's just go back to the triangle. So here I have my data Z1, Z2, and Z3. I have a Y. Of course, my Y's live inside here. But let's. So in this Y space, I'm going to imagine that Y is a point that's moving around. Z1, Z2, Z3 are fixed. Y is moving around. What I want to do is I want to write down a two form in Y space, which has the property that it has singularities when Y hits the boundaries of the triangle. Okay. So I'm trying to associate, obviously I'm trying to associate something with this region. Something needs to know about the boundaries, right? So I want it to have some kind of singularities as you approach the boundary. And again, since there's no units anywhere, let's say there's some variable going to 0 as you approach the boundary. What could it possibly look like in that neighborhood? It has to look like dx over x. Okay? It can't depend on anything else. There can't be any units. So it's got to be a form that in the neighborhood of every singularity, locally it looks like dx over x. Maybe if it's a 2 form, it has to look like dx over x times some 1 form, right? But the thing which is becoming singular, that part has got to look like dx over x. Then if I take a residue on x, I'm left with a 1 form. Now I'm sitting on the edge. Now there it has to have boundaries, and on its boundaries it has to look like dx over x, and so on. Okay? So a form that has that property, we say, if you're given a region, P, we say that we're looking for a form, given a region P, in this case the triangle, but given a region P, we're looking for a form omega P, which has logarithmic singularities on the boundary of P. Okay? Now, it's not obvious that such a form exists. Let me give you a simple example. Take a circle. So the region is x squared plus y squared less than 1. There is no form with logarithmic singularities because there's no 2 form with logarithmic singularities. Because the circle, you see, in order for this to make sense, this region needs to have codimension 1 boundaries, codimension 2 boundaries, and so on, right? The circle just has a codimension 1 boundary. So there is no 2 form with logarithmic singularities on the boundary of a circle. But there is a form with a logarithmic singularities on the boundary of a triangle. Okay? We'll write it down in a second, but I want to emphasize it's not obvious that such a form exists. But if such a form exists, it's clearly unique. And we'll make that more clear. All right, so let's just do it in the case of the triangle. And there's a very simple way of building this form, which allows us to introduce the concept of positive coordinates. In this case, it's extremely simple. But what you want to do is parametrize the inside of the triangle with some coordinates, 2 coordinates, because it's a 2-dimensional space, such that if those coordinates are real and they go from 0 to infinity, you cover the entire inside of the triangle. Okay? So in this case, it's really easy. For example, I can say y is equal to z1 plus alpha z2 plus beta z3. These are just the same good old-fashioned positive coordinates we were talking about before. I just fix C1 to 1, and I just say alpha, beta are real and positive. Okay? If I do that, I'm covering the entire inside of the triangle. Okay, there's some, I'm missing some pieces of infinity, but I'm covering the inside of the triangle. And now, when I have these positive coordinates, what is the form? Well, the form is just the d log, wedging together the d log of all the positive coordinates. The alpha over alpha, d beta over beta. That is the form, manifestly, with logarithmic singularities on the boundary of the region, in this case. Right. Now, that's what this form is, that's what the form is in these coordinates. Of course, I can write it in a more coordinate invariant way. I can solve for alpha and beta, okay, but I'll just write down the answer. It's y dy dy over y12 y23, y31, 1, 2, 3 squared. Now, there's nothing else this could be. It has to have poles when y hits 1, 2, 2, 3, 2, 3, 1, right? It's a 2 form, so, but dy isn't invariant, so the only way I can make it invariant, that this y dy is the only kind of invariant form you can have on the projective space. And then it has to have no weights under rescaling z1, z2, and z3, so there has to be the 1, 2, 3 squared upstairs. Okay? Yes?
I'm sorry, I think I just misunderstood your requirement. Can you explain the circle case? Why doesn't something like dr over 1 minus r wedge d theta meet your requirement?
Because d theta, the dr part is fine, but d theta doesn't have logarithmic singularities anyway.
So your requirement is that it has logarithmic singularities on but there's only one boundary.
No, that's the point. You have to have logarithmic singularities that has logarithmic singularities in the all the way down. Okay, so a prerequisite for this is that the object needs to have faces of all dimensionalities, starting from codimension 1 all the way down to nothing. Okay. Yeah, you could have looser things. You could say you don't care. Partial logarithmic singularities is an interesting notion. That might be relevant for generalizations beyond n equals 4 super Yang mills. N equals 4 super Yang mills has this feature that all the singularities have to do with the infrared, and eventually are just these logarithmic singularities. It's possible that we need to think about more general sorts of singularities that correspond to ultraviolet divergences, in which case maybe some notions like that would be important. What we're talking about is something that just has logarithmic singularities, all the way down. In any case, I'm just defining, I'll be defining what it is concretely. So in this case, when you have a triangle, it's just a d log of the positive coordinates, which if you like, you can write in this way. Now, once you know what it is for a triangle, what is this form with logarithmic singularities for a polygon? Right? Well, you can triangulate the polygon, and if you just sum, the omega is just the sum over all the elements of the triangulation of the omega I. Once we know what it is for a triangle, which is just the d log of all the positive coordinates, we know what it is for the whole space. And it doesn't depend on the triangulation. Okay. Because, why? Because this form has exactly the same properties as volume. Right? If you have a form of logarithmic singularities on the boundary of a region, if the regions are distinct and you add them, obviously the form is the sum of the two. And if they share a boundary, then the singularities cancel in the boundary that's being shared, and they only have singularities on the sum of the two of them. Okay? So any one way, for example, this way of decomposing the form, each term, that one will have a pole there, there, and there. But the next one will also have a pole there, and there, and there. So there has lots of poles that aren't really there in the answer. It's spurious poles corresponding to that boundary and that boundary. But they all cancel out. You're only left with something with poles on the whole boundary. Right? So in fact, this gives you a way of defining, for some spaces on which a form is defined, it tells you how to define it. If you can cover the space with a collection of positive coordinates, and you'll not be able to cover it with one of them, but if you can triangulate it, by triangulate we now mean cover it with a bunch of cells, each of which have positive coordinates. Then for each cell, the form is the d log of all the positive coordinates, and then you add them all up. And that defines the form of logarithmic singularities on the boundary of P, which is clearly independent of the triangulation. Okay? So that is our definition. So that's how, yeah.
So to define omega, you don't really need to triangulate, right? This is just...
In this case, so if by any hook or crook you manage to find a form with logarithmic singularities on the boundary, you're done. That's right. I'm just telling you one way of doing it. This is a way of doing it. Now, let me say quickly that this form is closely related. So the omega, so now let me tell you the relationship, in this case, between omega and the intuitive notion of area. So let's say you have some polygon. and there's y as a point. And I managed to compute omega one way or the other. So I'm going to write it as y dy dy. I can always do this. There's y dy dy times some f of y. Okay, f of y has some weight. Has some weight minus 3 when you rescale the y, so that omega has no weight. Okay. So now I'm going to tell you the interpretation of f of y. If you take this polygon and that point y, there's a Poincare dual picture to this. The Poincare dual picture to this, so the Poincare dual is where points become lines, lines become points. It's just, if you think projectively with upstairs and downstairs indices, remember things with downstairs indices were points, things with upstairs indices were lines or planes in general. So it's just flipping upstairs and downstairs indices. So if I do that, every one of these points now, every one of those points becomes a line. 1 becomes a line. 2 becomes a line. Okay? They become lines, so I have some other picture of a polygon. And y becomes a line. Okay. Also becomes a line. Now, what do you think the dual of y being inside the polygon, this polygon is? The dual of y being inside this polygon is that the line y is outside this polygon. So this is now a new polygon. The vertices here aren't 1, 2, and 3. They're the intersection of the line 1 and the, okay, so this is the line 1, the line 2, the line 3. So here's some A, B, C, D, E, F, and here's Y. This new polygon is still convex, but now Y being inside the old polygon is that the new line Y is outside the polygon. Right? So this is a dual of the original polygon. Now, when you're given points in a projective space and a line at infinity, that's the usual way of getting of doing the projection to identify the little two-dimensional vectors that allow you to draw it in Euclidean space, right? So let me actually go back. So in this case, say it like this. This is f of y, even for the triangle, right? It's 1, 2, 3 squared over y1, 2, y2, 3, and y3, 1. So let's just do this for the triangle.
So why do you have to consider this dual?
Sorry?
Why do you
I'm telling you in a second.
Oh.
Because I'm telling you that f of y is actually the area, not of the original polygon, but of this dual polygon. Okay. But let's just talk about this. Let's just talk about just this formula: 1, 2, 3 squared over y1, 2, y2, 3, y3, 1. Remember, this is our triangle with vertices 1, 2, and 3. Okay? But now, let me imagine a dual. So in the dual, here's the line 1, the line 2, and the line 3. They're intersecting on, let me call them A, B, and C. But, so what is y1, 2? So y is now a line. 1, 2 are lines, but that 1, 2 is then the point B. So this is the same as 1, 2, 3 squared. Let me just write it down like that as y dot B, y dot A, y dot B, y dot C. And furthermore, what is 1, 2, 3 squared? Well, that's just 1, 2, 2, 3, 3, 1, all epsilon together. So the numerator is just actually A, B, C over y dot A, y dot B, y dot C. And that's the high school formula of the area of a triangle. Because I imagine that y, if I imagine that y is a line of infinity, so I write y as, let's say, 1, 0, 0. yi. And I write the A, B, C, these guys. That's That's A, B, and C. If I write this as one little AI, or A, B, and C, then this formula is just equal to the determinant of 1A, 1B, 1C divided by 1. Y dot A, Y dot B, Y dot C is 1. And that's the high school formula for the area of the triangle. Okay. So we see that this guy is actually interpreted as the area of the dual triangle. So we have two notions. If you're given the polygon in the original space, we have a form of logarithmic singularities on the boundaries of that space. And we can define that by triangulating the space. That's one way. If you find other ways of doing it, great. There are other strategies you can think of doing it too, but the easiest strategy we know of is to triangulate the space and then define the form. However, the coefficient of y dy in that form has an interpretation as the actual area of the dual polygon. And that actual area now we can compute in lots of ways. I don't have to triangulate. I can just use Monte Carlo. I can throw darts. It's a real area. Okay. All right. So there are these two ideas: form of logarithmic singularities and volume. But it's the volume of the dual object. Now, in this case, a projective space, we know how to do everything. We can talk about it in the language of the form of logarithmic singularities. We talk about it as an actual volume. An actual volume of the dual object in this sense. Right? What we know how to generalize to the Grassmannian and what corresponds to calculating the amplitudes is the first picture, the form of logarithmic singularities picture. We do not yet know whether there's an analog of the second picture. Actually, we strongly suspect there is an analog of the second picture for reasons I won't have time to get into, but we haven't found it. I think finding it would be extremely important for the development of the subject for a number of reasons. That was actually a big obstruction for a long time, is that we were trying to generalize this literal notion of volume, which probably exists, but we still don't know yet. But it's this slightly more abstract cousin of it as a form of logarithmic singularities that generalizes easily. Okay. So we're starting to get there now. We're starting to get there. Associated even with the simple y equals c dot z amplituhedron. So associated with y equals c dot z. I will denote like that. That is our space. Associated with that now, we have a form, omega. It's a 4K dimensional top form in it's a 4K dimensional top form in GKK plus 4, and it depends as data. It depends as data on y and on the z's. And in fact, the only way the y and the z's ever appear is I can write it. So the analog of y dy dy in the Grassmannian is actually the following thing. And the only way the y's and the z's appear with each other here is through these combinations, like y1 through yk and 4 z's. So it's a function of these kinds of brackets. Right. Okay, so that's the geometry. And this is the form that depends on the z's that encodes all the structure of that geometry. The singularities of this object know all about the boundary structure of this object. Okay? All right, so we're starting to get there now. So now we're going to focus on this form for a while. So if I just want to get a number, for instance, I could look at f of y and z. F of y and z is some. F of y and z is some number. But it's a number that actually, first, it depends on y. That's one funny thing about it, right? And in the sense that if you're imagining the external data are the z's, then that f of y depends on y and the z's, right? That's one fact. Another fact is that the z's, as I go to higher and higher k, are becoming bigger and bigger vectors. Z's are becoming bigger and bigger vectors. Now, if we care about physics, we know that the z's should at most be 4 vectors. I mean, the sort of bosonic information in the z's is at most going to be 4-dimensional variables. So that already seems a little funny that there's a higher and higher all these extra variables. But even purely from doing something natural mathematically, it's clear that there's something nice that we can do. You see, we have this, the z's live in a 4 plus k dimensional space, right? So there's a big GL 4 plus k that is acting on. But the y's, a given fixed y, is picking out a particular k-dimensional subspace in the 4 plus k dimensional space, right? So if you have any fixed y, this y, I pick this particular k-plane in 4 dimensions, then, or let me draw it even better. Here's a k plus 4 dimensional space. And here's the k-plane y. Okay. Then the very choice of the k-plane y is breaking the GL4 plus k down, right? To a GL4 across a GLK, and the GLK is the GLK of the k-plane. Right? So the GL4k, the GL4 plus k that's acting on the z's, the thing that makes you think of all the components of the z's on an equal footing, the presence of the y's tells you they're not all on an equal footing anymore. There's the preferred ones of them that actually live in that 4-dimensional subspace. Right? So if I take the z's, part of the z's live in this 4-dimensional subspace that's orthogonal to the y's, and part of them live in the rest of it. Okay? So that's just a geometric fact. Right? So let's pick any given y. Let's pick a fixed y. So any given y by GLK, any given fixed y, I can bring to some form that I can call y naught, which just looks like a k by k linear transformation on the, so I have k y's, and I'm just going to bring it by the GLK plus 4 transformation to, sorry, just go. And the rest zeros. Okay, so let me bring the y to this form using a GLK plus 4 transformation, which I can always do. Right? And then, having fixed this as a GL basis, I can imagine that the z's have a top component, which is 4 z's, and k bottom components. For the moment, let me say the k bottom components, let me call them zetas. So zeta A1 up to zeta AK. So far, everything is still just bosonic variables. Everything is fine. Okay, yes?
Why is that zero?
Oh, because these are k plus 4-dimensional vectors, right? So I'm saying to specify the k-plane, you have to give me k plus 4-dimensional vectors. And I'm just saying take the first k plus 4-dimensional vector to be 1, 0, 0, 0. The next k plus 4-dimensional vector to be 0, 1, 0, 0. There's k of them, so I'm writing it like that. Okay, so I'm writing this y as a k by k plus 4. Perhaps in order to make it look more symmetrical to the z's, I should have drawn it on its side, right? So yeah, since I'm writing the z's as column vectors, I should have done the same thing for the y's. So let me write it like that. So this is k plus 4 and k. So I'm writing it like 1, 0, 0, 0, and then 0, 0, 1, and the rest are zeros down. This is y. Is that clear? See, now I'm not doing a GLK transformation, I'm doing a GLK plus 4 transformation, right? So we, huh?
It's on the z's.
Yes, so exactly. That's exactly the point, right? So I'm bringing y naught to this form, and that's distinguishing between the top 4 and the bottom k components of z. Geometrically, it's just saying what I said. there's a k-plane y, whatever it is, right? I mean, I'm not saying it's, I mean, I can bring anything to that form using GLK plus 4 transformations. So geometrically, I'm saying take the k-plane y. There's a 4-dimensional space orthogonal to it that I'll call T. And now the z's, some of them live in T, some of them live in y. And I'm just distinguishing between those two because the geometry tells me to, right? All right, still I haven't done much, but these zetas, I mean, I have this SL4 transformation on these guys. The zetas are just a continuous infinity of extra degrees of freedom I have, right? I just have this, you know, they're all continuous bosonic variables. So now what I can do is convert this extra information into the zetas into a finite amount of information instead of making it an infinite amount. I'll convert it to a finite amount of information just by declaring that they're all infinitesimal. All the zetas are actually infinitesimal. By infinitesimal, I mean that zetas to some high enough power are all equal to 0. Okay? Another way of saying what I'm doing is really I'm just doing a Taylor expansion of the entire result that I have, and I'm picking up certain coefficients of that Taylor expansion with a certain degree of with a certain overall power in the zetas, right? But one way or another, I have this form. The form exists. The form exists. It doesn't care about this distinction, right? But I take the form and I imagine doing a Taylor expansion in the zetas. Or if I want to say it another way, if I want to pick out coefficients with a certain net weight in the zetas, I can say that the zetas are infinitesimal, but zeta to some power is equal to 0. Okay. Saying that zeta to some power is equal to 0 is equivalent to saying that each zeta can be written in the form phi dot eta. Where zeta is bosonic, but phi is Grassmann, fermionic. And eta is fermionic. Both are fermionic. Now this I just runs from 1 to some n. Okay. And if I do that, then phi to the n plus 1, then zeta to the n plus 1 will equal 0. Okay, so that's how I've made it infinitesimal. Again, you can call it making it infinitesimal, you can call it doing a Taylor expansion and picking off various coefficients, it's all the same. Okay, so far so good? So now I'm saying that each CA has a top piece which is 4-dimensional, and the bottom piece is phi 1 dot A to A up to phi k dot A to A. Right. And again, I have this form omega, which depends on the y's and the z's. Okay. All right. Now, what can I do? What can I do with this form now that we've done all this preparation? Well, I can take this form and I can integrate it. But integrate against what? I'm going to integrate it to just completely localize it at some particular y0. So this is not really an integral. I'm just evaluating the form at some particular y0, but I'm saying it in an invariant way. Saying it in an invariant way, I'm integrating the form against some 4k dimensional delta function that projectively nails y to some fixed y0, okay, which I can always bring to the form that we just talked about before, right? Okay. In fact, if you have the form, it's actually trivial to do this integral, right? Because if we write the form in the way I told you, if we write omega by factoring out then this integral of omega is just equal to delta 4k of y nailed to y naught. This is nothing other than f evaluated at y naught. Okay. So this is just a one heavy-handed way of just saying evaluate the form. Evaluate that part at y naught. Right. This thing still depends on y naught and z. Right? But having now made the choice we made for the extra components of z, which are dictated by having chosen the y, what I can then do is integrate over all the phi's. If I integrate over all the phi's of f of y naught and z, now I'm finally going to end up with a function, so we'll call it a, which only depends on the 4 z's and the 4 eta's for all the external guys. And then it's extremely simple to see that the original objects we had were all projected, but this guy will have vanishing weight under rescaling z and eta. Well, in general, not have vanishing weight under rescaling z and eta by the same amount. Okay? Because if you rescale, because rescaling eta is the same as rescaling phi, right? Because they occur together as phi dot eta. Okay. So this thing will, in general, for general n, this thing will have non-zero weight under rescaling z and eta. But if you choose n equals 4, choose n equals 4, that 4 is the same as the 4 of the size of the z's. If we choose n equals 4, then this a, then it makes sense to group the za and eta a. I can call them some super za. And I have some function of the super za such that rescaling each one gives me the same guy back. So there's something natural about the choice n equals 4. I can make other choices. And there will be things that don't have that have weight, but n equals 4 is the special guy that does not have any weight under the rescaling. Okay. So I've now told you everything about how to take but I hope you see the non-trivial thing is the form. The form which depends on these big z's. That's the object. And once you have that object, what you do is you localize it to a point in y space. You make the part of the z's that are in the orthogonal complement generic. The part that live in y infinitesimal. And if you then pick off the coefficients, which is all that integration is doing, you get a function of bosonic and fermionic variables. It's only a vanishing weight when n equals 4. And so the resulting object is something with vanishing weight, this capital N equals 4. Okay. Now, in this way of talking about it, it is not obvious that this thing is supersymmetric. You know, it just looks like I have bosonic and fermionic variables.
So,
Yeah.
So why not in this formula use the unit matrix?
Yes,
with the
that's right.
unit
Exactly, that's right.
But you would choose that to be in some other direction, and all of this would go through if you would get this.
Exactly, because z is always defined relative to y. So what I was saying is a completely invariant, is a geometric statement. I just gave you some particular coordinates to make it.
There's no y not dependence.
There's no y not dependence. No. It's just saying that you have a form anywhere you are in y space. It's like spontaneous symmetry, right? Any choice of y, any y is dividing the k plus 4 dimensional space into 2 pieces. And all you're doing is saying make z generic in the orthogonal complement and infinitesimal in the other ones. And I didn't have to say anything about phi and all this stuff. That's just like a little bit of generating functionality to make it a little nicer. I could just say, don't even talk about infinitesimal, just Taylor expand into zetas. And then I get a zillions of functions, okay? And then you discover that all those zillions of functions, some of them are particularly nice. They have no weight under rescaling, right? So we're just picking off those guys that are particularly nice. Okay? And those guys have this simple interpretation. Right? Yes?
What is it that is making the bottom mark infinitesimal?
As I said, you don't have to make it infinitesimal. You could just say there's a top part and the bottom part. There's an infinite amount of information in the bottom part, right? So I'm just going to Taylor expand in the bottom variables. Okay, I can Taylor expand in the bottom variables if I like. And I'm telling you that certain coefficients of that Taylor expansion, mostly the coefficients will not have a nice weight under rescaling everybody, and some of them will. The ones that do, I've isolated in this nice way by saying that they're infinitesimal. Saying that they're infinitesimal with a certain rank is just picking off a particular component of the Taylor expansion. That's all. Okay. This of course, this is supersymmetry, as I told you before. But this is the sort of non-superspace way of doing supersymmetry. So we've done something which is secretly supersymmetric, even though at the moment it doesn't appear that it's supersymmetric. But in fact, not only is it supersymmetric, but if we go back to this original object, and we think about it a slightly different way, we'll see that not only is it supersymmetric, but it's in fact fully Yangian invariant. I mean, so it's giving us much more than all the supersymmetry. This expression is making all the symmetries of the object. Because let's decompose this y, right? So now I'm going to do this calculation in a slightly different way. One way we just did. I mean, it's just the dumbest way of it's the dumbest way of nailing y to y naught. But there's another way of doing the calculation. Actually, maybe perhaps before doing that, let me just do one quick example. Okay, just so. So and let me actually do an example that's relevant to the real amplitude. So with k equals 4, right? So let's say that we just have the case even k equals 1, n equals 5. Okay. So in this case, y equals c1, z1 up to c5, z5, and the whole y space is just the top cell of that G15, which is already 4-dimensional. Okay, so it's just the tetrahedron, nothing else, or the higher dimension, the 4-dimensional tetrahedron with 5 corners, nothing else, right? So in that case, y, so the positive coordinates are, for example, y equals z1 plus alpha 2 z2 plus alpha 5 z5 with alpha 2 5 positive. The form is the alpha 2 over alpha 2, the alpha 5 over alpha 5. And now the more invariant way of writing this form is exactly what you'd expect. It's y, dy, dy, dy. It's a 4 form over y, 1, 2, 3, 4. That's the singularities of all these boundaries. Y, 2, 3, 4, 5. Y, 3, 4, 5, 1. Y, 4, 5, 1, 2. Y, 5, 1, 2, 3. And the numerator is 1, 2, 3, 4, 5 to the 4th. Okay. So that's what this form of logarithmic singularities is. In fact, if I triangulate with any 5 guys, the form is always going to be the same, just replacing 1, 2, 3, 4, 5 with the 5 guys that appear in the tetrahedron. Okay. So this is our form. So now, how do we do our isolation? In this case, y is just a vector, so I'm going to write y as 1 or 0, 0, 0, 1. Write it like this. And the z's are going to be za, and down here it's going to be phi dot a. There's only one phi, but there's, well, the phi has 4 indices, but there's only one phi I into I. I 1 to I. Okay? So what is this? Well, So now I'm supposed to just extract this coefficient. And now let's look at what that is. First of all, what is the denominator? The denominator is trivial because the y just projects to the four-dimensional subspace up there. So the y 1, 2, 3, 4 is just the 1, 2, 3, 4 made out of the four-dimensional bosonic z's. Then I have 2, 3, 4, 5, and then I have 5, 1, 2, 3. So that's the denominator. The numerator is also simple because, for example, it's 5 dot, it's just expanding this 5 by 5 determinant. So it's 5 dot a to 1 times the determinant of the other guys, which is 2, 3, 4, 5, plus cyclic, plus 5 dot a to 2, 3, 4, 5, 1. Okay? Plus the other term, so the 4. So that's what it is. And now I have to do d4, 5 on that guy. But d4, 5, that guy is also simple, because this is 5 dot something to the 4th. Okay? But the integral d4, 5, this is just the Grassmann fact, standard Grassmann fact of life, of phi I, any theta I to the 4th is otherwise known as delta 4 of theta I. Any power of theta I. Well, that's a Grassmann delta function. Okay. So by the time I'm done, I now have what it dutifully looks like. I have something that looks like a superamplitude. I have d4 of a to 1, 2, 3, 4, 5, plus dot dot, plus a to 5, 1, 2, 3, 4, divided by 1, 2, 3, 4, 2, 3, 4, 5, 5, 1, 2, 3. And this is this famous R invariant in scattering element that's denoted in that way. Okay. Now, that guy, as written, is still not obviously supersymmetric, right? Well, it's some expression, right? How do you know if this is invariant into superformal translation, or whatever? Well, that guy is the most elementary object that you can get with the connection to the Grassmannian along the lines that we've been talking about for many years before. Because this guy can also be represented as dc1 over c1 up to dc5 over c5 modulo gl1 delta 4/4 c1 z1 plus c5 z5. And this form is completely manifestly invariant under SL4/4 transformations. So here you see that it's supersymmetric. In fact, it's more. It's a little bit more work. You see that it's invariant into the entire Yangian of both conformal and dual conformal symmetries. But anyway, here I'm just showing you that it's actually supersymmetric. And in fact, that's something that we can see, that connection between the first way of getting it, which is what we just did, and this Grassmannian representation, Grassmannian-like representation is actually universal. So in order to see why, let's go back and let's say that I'm computing omega. Let's say I'm computing omega by summing over some sort of triangulations. But in each triangulation, what I've succeeded to do is to write y as some C alpha ZA, where the C alpha depends on some parameters, alpha 1 through alpha 4k, where these alpha 1 through 4k are all positive. So that's the point, right? We're supposed to parametrize it in terms of a 4k dimensional cell with positive coordinates, right? Okay, so in each one of these cells, there's some particular way of doing that parameterization. And the omega for that cell, the omega for this cell would just be the d log of all these coordinates, the alpha 1 over alpha 1 over the alpha k over alpha k. Then in that way of parametrizing it, it is a very simple exercise that I won't go through to show you that there's a different way of, there's just if you parameterize y like that and you carry out the integration that we talked about with y to y naught, and you integrate over the phi 1 to the d4 phi k, then you discover that this is nothing other than the d alpha 1 over alpha 1 is d alpha 4k. So let's say for the I component of that form, up to d alpha 4k over alpha 4k, delta 4 slash 4, or delta 4k slash 4k, of the c's that depend on the alphas dot z. So each one of these pieces of the triangulation is actually directly giving you this manifestly supersymmetric formula, which is the integral of the d log of positive variables of the positive Rashmanic of this d log form times delta 4 slash 4 c dot z. These formulas were the ones that we've been staring at and playing with for a long time. Okay? So now we can interpret these as nothing other than another way of doing the same localization of the form to 1. Okay, so and that's how you see that this object is supersymmetric. And not only supersymmetric, it's actually Yankee invariant, because you connect it to the entire previous story that we had and everything that we knew about it. Okay, so yes, sorry?
Is the conformal invariance sort of tied to the fact that you give the projector space?
Yes. Yes. Yes, absolutely. Yes. We can all go hand in hand with each other.
So this probably would not work for a non-conformal theory.
Well, for non-conformal theories, we have additional data. We have some lines of infinity that we have to also keep in the problem, and so one has to see how that's going to enter the subject. So, yeah. Okay. All right. Anyway, so I did that very concretely, just so we see how it works, at least in some simple example. But let me summarize the situation again. This is for trees. So we have this object. So this is just something that lives, this is a region that lives in GK plus 4. And you could just study it, and you could just see what does the geometry look like, and it has these nice boundaries, and it splits as you go to the boundaries, and there's all these wonderful properties. You just study the region for its own sake, right? Then there's something associated with it. Associated with this region is a form with logarithmic singularities on the boundary of that space. Right? So if I call this the amplitude of n and k, then there's a form associated with n and k, which has logarithmic singularities, depends on the y and the z's. There's log singularities on boundary of a and k. And it naturally divides the k plus 4-dimensional space up into a k-dimensional part and a 4-dimensional part. Sorry. I don't know why I repeated that. A k-dimensional part and a 4-dimensional part. And so we have z's that are generic in here and are infinitesimal in here. And so if I take this form, I localize the form anywhere, and I integrate over the phi. Claim is that this is the tree amplitude. And the second way, and the two ways of writing the form that I just told you a second ago, makes it manifest that this tree amplitude is supersymmetric. It's in fact Yangian invariant. Okay. and furthermore, it's also clear that questions like where are the singularities, you see, if you ask a question about amplitudes, you say where are the singularities, you imagine you're moving the external data around in order to, let's say, approach a factorization channel, right? But in this picture, the external data is fixed, and the thing that's moving around is y. Because ultimately, there is some invariant which is going to 0, right? And instead of imagining y is fixed and moving the data around, you imagine the data is fixed and you move y around. Okay? And so it's clear that the only singularities that this object can have is when y approaches the boundaries of A, right? Because it has logarithmic singularities on the boundary. So that's why the question of the singularities of z turns into what the boundaries of the amplitude look like. And then if we track through everything I told you yesterday, you can see that the splitting apart of the space implies the specific factorization of this ultimate function, which is exactly the one you need for the amplitude. But that's just some bookkeeping to see that all happens. All right.
One question.
Yes.
You mentioned this Yang, it's kind of hard to see here, but a little bit about the Yang. So one parameter definition of that, find the algebra. So there's a parameter.
Yeah.
What's the parameter here?
Yeah. So that's something that in this story we don't know the answer to, but along the lines of the sort of along the lines of looking at what each individual building block looks like. The things inside the actual Rosmanian. There are some people who are starting to talk about how you might decorate these bipartite graphs that give you the cells of the Rosmanian with something that looks like a spectral pattern. Anyway, there are people who are starting to explore that. I haven't studied it myself, so I don't.
Yeah, the 2D global theory.
Yes, yes, no. So here we have everything undeformed. So everyone who knows what you know says that this should be deformed somehow, right? What is the deformation of this? What's the deformation factor? What's Q? And yeah. So I don't know. I mean, maybe some of my colleagues will know immediately, but I certainly don't. Okay. So any questions about this? All right. So then I think I will end by just I'll end by defining what the first by motivating loops and then telling you what the loop level amplitude is.
Maybe I have one question.
Yeah.
So if you use this form without doing triangulations,
Yes.
does it give you new representations for the
Yes, absolutely. Absolutely. Which are not BCFW, which are something new. In fact, in many cases, so when we have a volume interpretation, when we have a literal volume interpretation, for example, what you can do is triangulate the dual polygon. Or you triangulate the dual polytope in general when you go to higher dimensions. That gives you, as we did with Freddie and Andrew and Yara and Jake 2.5 years ago, following on what Andrew himself did to recognize the NMHV amplitudes as its volume, you can directly triangulate the dual, and that gives you totally new representations of the amplitude that are manifestly local. And in fact, there are many reasons to suspect that a volume-like formula exists, and one of them is that we've had BCFW formulas at tree level and at loop level, but especially at loop level, we have really nice local formulas, which look like they're triangulating something. But surely they're triangulating this in another way, but we don't know what the volume is that it's triangulating. And there's tons and tons of, well, not tons, but there's a number of other circumstantial pieces of evidence that it really is a volume somehow. For example, the forms are actually positive. Those functions f of y, they all turn out to be positive. If you take y inside the polygon, and you actually inside the positive region and you compute them, they are positive. That fact is not obvious from the triangulation form. See, if you have y inside, when you're adding up the area of all the little triangles, sometimes y is inside, sometimes y is outside. So some terms are positive, some terms are negative. And yet the whole thing is actually positive. What makes it obviously positive is the dual representation, where it's an actual area of this dual object. So anyway, so those are the yeah. So that's why we're sure that there is some second way of representing it still. It's probably very important to find what it is, but we just don't know how to do it. But yes, indeed. But even if without that, you found yet another way by hook or by crook, and we have some strategies. There are sort of 3 strategies that you see already for the polygon for how to determine this form. And you know, one of them we know how to generalize in complete generality, and the other one we have we're starting to learn how to do. But yeah, any way that you can do it will give you some new representation for it. Yes. Okay. So let me just motivate why would we think about loops. And again, we're just thinking just mathematically for a bit. But you might take this object and say, look, really what we have is we have this. So this is just motivation. I'm going to motivate another kind of positive structure. Okay. And so it's not. So what we're going to do is we're going to ask a question. We'll see that this question implies a certain positive structure, and then we'll just study that positive structure for itself after having been motivated by this. We'll interestingly find that that new positive structure is more general than this. So this, what I'm about to motivate, will give you some subset of it. So this is just some motivation for looking at a certain new kind of positive structure. Okay. But let's say. So it's clear that this A and K, they all sit as faces of N and K go to infinity of some master object, right? So what if you want to start with that master object? But instead of going to a face and then a face and then a face to go down, you just want to manually, you want to excise a bunch of those particles that you're not looking at, right? So what do I mean by that? I mean, let's say I have this big K by N matrix, and it has, you know, a huge number of particles. But what I want to do is I want to pick one of them and just ignore it. Just one particle for the moment and ignore it. What do I mean by ignore it? Let's say I want to pick particle n. Let me put n plus 1 here, and then 1, 2, up to n. I'm going to ignore particle n plus 1 means that in the C matrix, this is supposed to be the C matrix. Well, whatever that column is, I can set it equal to 1, 0, 0 by GLK transformation. I can set it to that. Okay. And by ignore it, I literally mean ignore it. Chop it up. So now I'm going to look at this smaller matrix. Okay. I chop it up. I look at that smaller matrix, but there is some memory of the fact that that guy is there in the structure of the matrix which is left. In the matrix that's left, remember, all the minors of the original matrix are positive. Okay? So because all the minors of the original matrix are positive, then first of all of these minors down here are positive. Right? Because of the minors corresponding to that guy. And also, these bigger minors are also positive. So 2 sets of minors are positive. If I just forget about this guy, I didn't know about it, someone handed me this smaller matrix, then there's 2 positivities. All of these minors are positive, and these bigger minors are positive as well. Okay? Now, that's fine. But now let's say I want to ignore more than one of them. Okay? If I want to ignore more than one of them, now I have a problem. Because, well, and by the way, if there's just one of them, well, it doesn't matter where I put it, right? I can put it anywhere I like. But let's say there's 2 of them, right? So there's going to be one guy here, and there's going to be some other guy there, and I want to ignore them. But now I have a problem, because the minors involve this guy and that guy. Let's say there's 3 of them, some other guy. But if I just look at the matrix that's left, whether the minors are positive or negative or whatever will depend on the ordering of those individual guys that I was talking about, right? So that's some artificial extra information that I would have to add by hand. So far, there's just the ordering of the external particles. Now we're talking about a different ordering, an ordering of the guys that I'm trying to ignore. Totally different structure, right? So there's some additional data that I would have to give if I wanted to pursue that. If I want to ignore one particle at a time, it doesn't make any sense, unless I give some ordering for the particles that I'm ignoring. Okay. But I can do something else. I can ignore 2 particles at a time. So let's say I'm going to ignore the 2 particles, and I'll call them A and B. And so ignoring them is going to be the same. I can always fix so that that looks like that, and the other one looks like this, and I have the rest. Now the positivity has the property that all these bottom minors are positive because of that guy. And again, all the big minors are also positive. Right? So these things are positive, and any of the bigger minors are also positive. Right? Now here too, it doesn't matter where I put it, just 2 of them, so long as I put them right next to each other. Right? But now let's say I take another 2 guys and I put them right next to each other anywhere else. Okay? So just for the heck of it, let me call them C and D. And just for the moment, let me put it right next to the guys that I was ignoring before. So now let's look at the resulting structure. Now, once again, all the minors down here are positive. All the minors of this, when one of them is positive. All the minors of this, when that guy is positive. All the minors with all of them are positive. Okay. And now it doesn't matter where I put C and D. Let's say I move them anywhere I like. I still excise them. I look at the remaining guys. Because I've moved 2 guys together, because it's 2, there's no signs. So I can put them anywhere I like. So if I want to hide individual particles, it doesn't make sense. I have to tell you the order in which I was hiding them. But if I ignore pairs of particles, I can put them anywhere I like. And hide literally means just look at the matrix, excise them, look at what's left. And if I do that, I get what looks like an interesting structure. In general, what I'm left with is a k-bion matrix down here. So this is N. It's a k-bion matrix down here, called C. And then a whole collection of 2-bion matrices. D1, D2, up to DL. So this is 2L. Capital L is just the number of those that I have. Okay? And the memory of how I got there is that for any L prime that's between capital L, little l, between capital L and 0, if I look at the minors of C plus any L of the D's are positive. That's the new positive structure that we're talking about. Okay? So that motivates looking at this new space, not just k-bion matrices, but this is still, it's the analog of the positive Grassmannian now. We haven't talked about the Y's yet. Okay? We're just looking at inside the positive Grassmannian, we can look at positive k-bion. We can look at positive k-bion matrices mod GLK. We can add a collection of 2L 2-bion matrices mod GL2. And demand that the minors of C together with any one of the D's is positive. So the C's alone are positive, the C's with one D are positive, the C's with 2 D's are positive, and so on. Now, this corresponds to something simple geometrically. You see, because the only minors that I'm talking about are C corresponding to any number of the D's, but there's always a C in there, that means that if I take the D's and I shift them by any linear combination of the vectors and the c's, I'm not changing anything. Okay. So the space in which the c plus this collection of d's lives is actually the following. The space is the space of k-planes in n dimensions. So here, now, I have a k-plane in n dimensions. So here's k. Here's n minus k. So I have a k-plane that's living in n dimensions. So that's n and k. It has an orthogonal complement, C orthogonal, which is n minus k dimensional. And what I'm doing in that orthogonal complement is I'm putting L2 planes that live in that orthogonal complement. So D1 through, so these are sort of 2 planes that are living in the orthogonal complement of C. Now, in order for those 2 planes to be interesting and really be full 2 planes, n minus k needs to be at least 4. It needs to have 2 planes in at least 4 dimensions for them to be interesting. So that's why, remember, n has always got to be greater than or equal to k plus m in order for the z's to fill out the space in which they live, the collection of z's to be space filling in k plus m dimensions. And so this structure only becomes possible for the first time m equals 4. M has got to be greater than or equal to 4. So you have to have m greater than or equal to 4 in order to be able to usefully find this positive structure that's motivated by hiding pairs of particles in this way. So the minimal case is m equals 4. And if we put m equals 4, then everything is fine. C perf is at least 4-dimensional. N minus k is at least 4 or bigger. So there's plenty of room to stack as many 2 planes as you like, living in that dual, living in the dual n minus k dimensional space. Okay. So now this is the analog of just the positive Rashmanian. Remember, so we have the positive Rashmanian. Now we have this bigger notion of positivity, which doesn't just involve the n minus k space, but involves the n minus k space together with a collection of 2 planes, the k dimensional plane, but the k-dimensional planes with a collection of 2 planes in its orthogonal complement. But now, what is the image of this going to be under y equals c dot z, the analog of y equals c dot z? Okay. Well, what it's going to be, when I have y equals c dot z, if we just go back to this, remember what this ended up giving us is a k-plane in k plus 4 dimensions. So here's the k-plane y in k plus 4 dimensions. But we have sitting here emptiness, nothing in this 4-dimensional subspace, right? So what's going to happen is that if I now define y equals c dot z, and then so I put the indices, y alpha I equals c alpha a, z a I. And I also define, let me call it A gamma. Gamma is going to run from 1 to 2. This is going to be associated with the D's. A gamma I equals D gamma A ZA. Exactly the same thing. Now I have one of these for each loop variable. Okay. So these A gammas, gamma runs from 1 to 2. Okay. And there's L of them. So this is the bigger space now, where C and D satisfy these new positivity constraints. Then what are the A's? What space do the A's live in? Well, exactly because the D's are only, there are 2 planes, but they're defined modulo shifting by anything in C. That means that the A's are only defined modulo by shifting anything in Y. And so they're interpreted as 2 planes that live in the 4-dimensional space orthogonal to the Y's. Okay. So I have L2 planes, A1 up to AL, that live in the orthogonal subspace, 4-dimensional subspace to Y. So that's the analog of GKK plus 4. We have GKK plus 4. That's what we had before, but now we get to put, we have a slightly bigger space. Not just k-planes in k plus 4 dimensions. It's k-planes in k plus 4 dimensions with a collection of L2 planes in the complement of that k-plane. Right? And in that space, there is a positive region. There's the analog of the inside of the polygon, and the analog of the inside of the polygon is this guy. Right? So now my omega depends on y and on these L lines, AI, as well as on the z's. Now I have a form of logarithmic singularities on this space. Those L lines, how many degrees of freedom are associated with each line? It's a two-plane in 4 dimensions. The dimensionality of G24 is 2 times 2 is 4. So there's 4 degrees of freedom associated with each one of those 2 planes. That 4 is the same as the number of degrees of freedom associated with each loop variable. And so this is giving us the integrand. Omega is the integrand for the L loop amplitude. So, just as before, this space was the tree level amplitude. This bigger space, this is now defining the amplitude for N, K, and capital L. So that's as a space. Once again, you can study the space for the heck of it. You can discover studying this space the other singularities that we need at loop level for unitarity emerge. Okay, I won't go through that exercise. And again, you have to find a form of logarithmic singularities on the boundary of that space. And once you do, you do exactly the same thing as we did before. Now notice that the only integral is still over y, right? Again, these a's are just like the top component of the z's. They just live in the orthogonal complement of y. So we just nail y. We just nail y to y naught, and we integrate over the phi's. So that's all we do. And after we do that, so if we do the integral d4 phi 1 through d4 phi k of the integral of omega delta 4k of y and y naught, we're left with an m, which depends on the z's and depends on these L lines, L2 planes, A1 through AL, and that is the loop integrand. Yeah.
So the conditional possibility of these, can you remind me? Actually, just like the GL, G2.
Sorry, what did you say? What was
The conditions of possibility of D, do they depend on C? I don't remember that.
Yes. So the conditions are exactly what I said. So let me finish defining. Yes, thank you. Since I'm summarizing here. So y equals c dot z, a equals d dot z, and if you pick any L between capital L and 0, then the ordered minors, as usual, the ordered minors of the matrix that you get by C plus any LDs are positive. So you can just take the minors of C are positive. Then you can take one of the D's. The minors of C and one of the D's are positive. All of them, right? Okay, or 2 of the D's and so on. Okay.
So D is the region of G2.
Yes, D is the, so where that 2 came from in this hiding picture was that we were forced to hide 2 particles at a time. And we're forced to hide 2 particles at a time for a variety of reasons. I told you one of them. One of them is that if you don't, once you start hiding many things, there's this arbitrary extra ordering that you have to put in. So you can't do the simplest thing, just do 1 at a time. You can do 2 at a time, okay? And that's minimally in m equals 4. Now actually, so you can generalize the whole structure mathematically if you like. Go to higher m. As long as m is even, the tree object makes sense. And even the loop object makes sense. You could start hiding 4 guys together at a time, or 8 guys together at a time. Or you could hide any even number of guys at a time. And I have no idea what those things correspond to. There's some generalization of loops to other situations. Yeah.
Can you remind me why? Because the difference between M and even and odd comes from the...
From the cyclic structure, yes.
And what do we use the cyclic structure to define omega? Or
Well, omega just has a cyclic structure because the amplitude itself has a cyclic structure. So, yeah, so that's why the amplitude in the end is cyclically invariant.
So what goes wrong if n is odd?
You just get something that's not cyclically invariant.
So ultimately, how do you know this is the amplitude?
Huh?
How do you know the amplitude? Just because it satisfies all these constraints?
So ultimately, well, I mean, really it's because you check. You check large amounts of multiple examples. But officially, you check that this definition has exactly the same singularities that the amplitude is supposed to have.
Sort of reduced.
Right, exactly. And you know, the status of that check is kind of intermediate. Because what I showed you yesterday, even at tree level, is that as we go to the boundary, it sort of splits, that the C matrices split in this nice way with the lefts and the rights. But there's still some sort of fine print that we really have to prove, that the image of each one of those L and R regions don't overlap each other in GKK plus 4, that they naturally, you know, so if they overlap, then it wouldn't be true anymore. So some of those things we haven't, I mean, I don't think we've proven. But there's definitely a lot to be done just mathematically to really clean it up and beautifully understand what the boundary structure looks like, even before getting into the form and all the rest of it. But that's but conceptually that's how it should be proven. Practically, you just check it zillions of examples. It's very non-trivial. So let me actually just end by giving you the simplest version of what the amplitude is for the 4-particle amplitude. K equals 0. The 4-particle amplitude, but now with any number of loops. So K equals 0, tree level is just 1. There's nothing going on. The amplitude is 1 in this language. Two more things. Sorry. Two more quick things. One of them is that you'll notice that this notion of the positivity of the external data and all of that was sort of crucial for defining this shape, right? Once we define this shape, we define this form associated with the shape. There's a form that has logarithmic singularities on the boundary of the region. But now that we have the form, we can forget about the fact that the external data was positive. Now that's a form that's even complex. It's totally well defined anyway, right? So so the fact that we have to take the data into this positive part in order to define the object doesn't mean that we're only computing the amplitudes when the external data is positive. That's good, because the external data being positive here corresponds to even being real, never mind positive, corresponds to being in 2,2 signature. So we're not saying that you can only compute amplitudes in 2,2 signature. But we are saying somehow that the amplitude is naturally defined in 2,2 signature. Okay? The amplitude is the answer to a really nice question when the data is in 2,2 signature. It's the answer to the question of the volume of the amplitude. Or this form notion of the volume of the amplitude. But somehow that continues away from 2,2 signature to anywhere we like. So that's one. The other one is I still haven't told you exactly how these Z's are related to the momenta of the particles and things like that. Okay, and okay, that's part of the dictionary that you could even in principle read back by continuing to develop, starting from the mathematical line. But these are the momentum twistor variables of Hodges. And so there's a very simple algebraic way of going from the actual momenta to these momentum twistor variables. So, okay. All right, so let me just give you the simplest example. So let's say we're doing n equals 4 and any L. So now all I have, that I don't even have any C. I just have L 2x4 matrices, right? And first, each 2x4 matrix all by itself needs to be positive. Okay. So now it's really simple to make 2x4 matrices that are positive. There's this sort of convenient way. Remember, you can gauge fix any two columns to be 1, 0, and 0, 1. So let me gauge fix column 1 and column 3. Here's 1, 2, 3, 4. And also, sorry, notice that in this case, the positivity of the z's is basically irrelevant because I have 4 z's, they're living in a 4-dimensional space, they're living I have 4 z's living in P3, and I can always do a GL4 transformation to put them to the form 1, 0, 0, 0, 1, 0, and so on. Okay? So the positivity of z's is not even playing a non-trivial role here. So in a sense, this is the case where the novel positivity associated with the loops is the only thing that's going on. In general, there's that, together with the positivity of the external z's and all the rest of it. But here, all we're seeing is the positivity associated with loops and nothing else. And so now I'm really writing down. So now I'm just writing down all these D matrices that are the same as giving me the A's, because the Z's have been fixed to the identity. But there's this trivial way of making the matrix positive. Okay. So that's the way of parameterizing this 2x4 matrix, and you can trivially see that all the minors are positive. Okay. 1, 2 is 1, 1, positive, and the only non-trivial one is 2, 4, which because of the minus sign there is also positive. Okay, so all the minors here are positive. And so I have L of these. What we call D sub I. I have L of them. And all of them are positive. But I also have to take that if I take any 2 of the D's, and I look at that minor, it's also positive, right? So if I take this 1, 0, xi, yi, 0, 1, negative wi, zi, 1, 0, xj, yj, 0, 1, negative wj, zj, that this 4x4 minor is positive. So we can compute that 4x4 minor, it's a trivial calculation, and you find that it's xi minus xj, zi minus dj. So let me put it up here, the condition. So these have got to be positive, and also xi minus xj, zi minus dj, plus yi minus yj, wi minus wj is negative for all I and 6. And that's it. There's no 6x6 minors, they're all 0, right? So the biggest I can make are 4x4 minors. Right? So this is a nice 4L dimensional space, right? For each loop order, I have 4 variables, x, y, z, w, and you just have to study this space. You have to triangulate this space. And triangulating that space is the same as solving a 4-particle amplitude to all loop orders. If you can triangulate to all loop orders, and because triangulating it means I'm going to cover that space with a series of positive coordinates. The form for each region is just a d-log of all those positive coordinates, and then I sum over all of them. So if you succeed in triangulating it, you succeeded in solving for the amplitude, or solving for the integrand of the amplitude. But I mean, this is, as I said in my colloquium, it looks like a junior high school geometry problem. Okay? I can make it look more like a junior high school geometry problem if I just define little 2-dimensional vectors A to be x, y, and B to be zw. And so this is like, you have the 2-dimensional plane, you have the upper quadrant, you have A-like points, these are A's. You have B-like points, which I'll write as X's, and we have to have that they're all in the upper quadrant, and also that AI minus AJ dot BI minus BJ is negative, which just means that if you draw the line from 2 A points, let's say A1 to A2, and the line is going like that, then the B's have to be arranged such that the line from B1 to B2 is obtuse to the line from A1 to A2. They always pass through each other in opposite directions. That's it. You have a collection of points in the upper quadrant. They're moving around with the constraint that the line from 1 to 2 for the A's is always going in the opposite direction as the line from 1 to 2 for the B's. Okay. You find that space, you've solved for the loop amplitude. Now let me make that a little more concrete. We could actually spend just 5 minutes, but I don't want to do just even a little bit of tedious algebra on the board to just compute the 2-loop amplitude like this. Okay? So there's just sort of 3 regions and you just find them and you add up the forms and you get the right answer. But instead of doing that, I want to show some simpler things that we can see to all loop orders actually. So if you want to classify the whole region, and I should also say that even without solving for the whole problem, you can see what some of the singularities of this space look like. So the cuts of the for loop integrand correspond to, degenerating some of these conditions, going to the boundaries of this region a little bit. In particular, the cut that corresponds to a unitarity cut, where you think you should see something like this happen. 1, 2, 3, 4. That corresponds to taking one of these loop variables and putting one of the A's, the A for that guy on the x-axis and the B on the y-axis of this plot. Okay? And then what you can do is you do that. You take one guy, you put his A on the x-axis, the B on the y-axis. You look at what these inequalities look like, and you find the inequalities separate into two sets with shifted points in exactly such a way so we produce this picture. So for that to happen, there's a sort of remarkable little identity involving all these minors that has to be true, which is true. But I'm saying even without solving for the whole problem, you can see that going to the unitarity cut splits it in exactly the way you would expect from unitarity. So again, we can see the sort of textbook unitarity follow directly from positivity, even without having solved the whole problem. But yes?
Question. So you said this object is an integrand.
Yes.
What's the integration variable?
The integration variables are exactly these guys, x, y, z, w. So the form that I'm finding. So let me give this example, and then I'll do the example, and then you can see. Okay. But actually, so let's look at an even simpler. Let me look at an even simpler thing. What I want to do is, let's say I'm going to put all of the A variables on the x-axis, right? So that's going to be some other cut, right? I'm going to put all the A variables on the x-axis. So that's saying I'm going to put all the yi to 0. Right? So that's putting one constraint on each one of the loop variables, right? So what could it be? Each loop variable I'm cutting one line on each loop variable. And what this is doing is cutting the propagator on the 1, 2 side. Okay, so this is a sequence of single cuts. Right? I have L loop variables and I'm single cutting all L of them. Now, if you happen to know something about n equals 4 loop amplitudes, you know they're built out of these pictures with boxes and this and that, you know a lot of other things, you know that there's a unique, only one set of topologies that could possibly contribute to this cut. And these are the famous ladder diagrams. Okay. So I'm just giving you a peek ahead of time where we're going, but if you cut every single loop variable is cut in that way, then the only one of all the possible diagrams that could contribute is that one. Okay, so we have some idea of what it is that we're trying to get. But let's see how it comes about here. So let's say that all these y's are 0. Then what happens to my one non-trivial constraint? My non-trivial constraint just becomes xi minus xj, zi minus zj is negative. The other term is gone. Right? So now this simplifies greatly. Okay. So first, the w's are totally unconstrained. Right? So what is the form in the w's? It's just a d log of all the w's. They're just all positive. So that part is good. So I have dw1 over w1 up to dwn over wn. But this is also trivial. This is telling me that let's say without loss of generality, I can say that the x's are ordered such that x1 is less than x2 is less than x3 up to less than xn. Of course, I can then sum over all the permutations, and I get all of them. Let me pick one order. Let me say that x1 is less than x2 is less than xn. This inequality tells me that the z's have to be oppositely ordered. Right? So I have to have z1 bigger than z2, bigger than zn. Okay, so now I want to find a form in x and z space with logarithmic singularities on these boundaries, right? Well, these. Oh, so what is that? What is that form? Well, x1 is the smallest, so x1 just has to be positive. x2 has got to be bigger than x1. Now, let me be super heavy-handed. Here are some positive coordinates. x1 itself is a positive coordinate. x2 is x1 plus sigma 2, where sigma 2 is positive. Okay. So the form here would be d sigma 2 over sigma 2. Well, but that's just the same as dx2 over x2 minus x1. Okay. So it's what you'd expect. So you have dx2 over x2 minus x1, dx3 over x3 minus x2, and so on. dxn over xn minus xn minus 1. Right? And the other way around for the z's. So let me complete it here. So it's dx1 over x1, so dxn over xn minus xn minus 1, dz1, dZn over Zn, dZn minus 1 over Zn minus 1 minus Zn, all the way up to dZ1 over Z1 minus Z2. Okay. So now you see that is a 3L form on WXZ space with logarithmic singularities on this boundary. Okay. And that form is exactly that type.
So what's the external data in this?
The external data is all gone because I fixed the z's to 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. So it's just taking care of the specific. That's right. No, it's not specific. I mean, it's general, but because there's only 4 points, you can always. Yes, that's right. That's right. So in fact, yeah.
You have about a little less than.
No, so I'm done. I'm done. So what happens is, in fact, let me just tell you what's going on. This 1 over x2 minus x1 and z1 minus z2 is that internal propagator. The next one, so I can pair them up as I go along. The next one is that internal propagator, that internal propagator. So it's all the internal propagators. There's an x1 naked at one end, which is that guy. There's the zn on the other end, which is that guy. And there's the w's, which are all of these guys. Okay. And so that is exactly just the ladder. So now, the thing which is sort of interesting is nowhere here do we talk about diagrams, planar diagrams. You know, there's nothing that looks like it's just a problem that's directly defined in the space that it lives, and you solve it. And remarkably, the fact that it gives you something that can be interpreted as planar diagrams and all the rest of it is all helpful. Okay. Now we've succeeded in actually triangulating the space by hand at low loop order, and check that it gives you the answer. There's probably some idea needed for sort of trivializing these positivity conditions in general. This is the analog of something I didn't have any time to talk about, which would be a huge topic by itself, of parametrizing positive k by n matrices, even for the positive Rashomonian. And there too, if we didn't know anything about, if our mathematician friends didn't exist, it would have probably taken us some time to figure out that there's this nice way of parametrizing the Rashomonian with positive coordinates so that all the minors were positive. Well, we're in an analogous situation, except they haven't told us what to do yet. They haven't thought about it. How do we parametrize these things to make these positivities manifest? Perhaps if we do that, it will make it easier to triangulate the space and understand it. But what we can do, and have done, to sort of check that everything works, is here I told you a very trivial cut, but we can start computing all sorts of other cuts. So sort of all sorts of simplifications of this problem. They all correspond to exploring different faces of the amplitude in this case. So all sorts of different facets of it. And so there's all kinds of cuts that we can compute to all loop order. Many of which, and here it's trivial, there's one term, but many of the other ones are totally unobvious from any other point of view as far as we can tell. But we can match them up to the known expressions in the literature through the 5 loops, and so it works with 5 loops. It's probably correct. Okay. So that's. But anyway, it gives you a flavor of the sort of very simple sorts of positive geometry problems that are being made equivalent to the computation of Nima. Okay, so that's all I want to say. That's really it. I finished defining the object and telling you some things about it. The 2 very big things that are missing, many very big things that are missing, But obviously, we'd like to go with the theories that are less supersymmetric, not so much, well, mostly because of the really new ingredient isn't so much supersymmetry, I don't think, but the fact that n equals 4 doesn't have ultraviolet divergences. And the second we go to less supersymmetry, there will be ultraviolet divergences, and there has to be some other structure which is taking care of all the magic of the renormalization group that we understand so beautifully from the standard perspective of local quantum field theory as invented here by Wilson. So, I mean, so that's such a glorious way of thinking about the physics of the ultraviolet that if it's going to come out from some other picture, it has to have something truly magical in it to be able to reproduce the normalization group. So that's one very big thing that's missing. The other obvious big thing that's missing is that this is all connected to the planar limit of the theory, which has associated cyclic ordering of the external particles. And yet, we know from many points of view that there's even more magic beyond the planar limit, not less. There's even properties of the planar answers that are mysterious to a planar person that only make sense when you realize that it's embedded in a theory of finite n. There are relationships between all these different planar sectors, identities that are satisfied between them, that are mysterious from the point of view of just one sector at a time, and make sense only when you see it as unified in the bigger structure. And of course, most wonderfully of all, we know there's like absolutely glorious structures sitting there in gravitational amplitudes. Now, this entire subject, this entire line of thought began with Freddie constantly emphasizing that the VCFW recursion relations were writing the amplitude as the sum over simple terms, each one of which had spurious folds, and that because there are spurious folds, there's no local interpretation for each term, yet magically they cancel in this sum. Right? So where is that coming from? Now, one attitude you could take is, well, all the magic is you're just doing like, it's field theory. It's field theory. It's the usual way of thinking about field theory.